Welcome back. This is Statistical Process Control 201. This is the sophomore level. We've finished our discussion of calculating sigma, and we're going to begin our discussion of understanding how to actually do statistical process control charts with various kinds of data by trying to understand the significance of the standard deviation, or sigma. So just quickly to review, we recall that sigma, or the standard deviation, is equal to the variance, the square root of the variance being the sum of all the squares of the differences between observations and the mean of all the observations squared, the sum of those differences. That's the distance here, that distance, this distance, this distance, this distance, all squared, right, to get the sign right. The sum of all those squares divided by the number of observations minus 1, and then this is the variance, and then to get the standard deviation, we take the square root of that, and we call that sigma. All right, well, that's all well and good. You recall that we chose 2 sigma control limits here for our process control chart. Well, why do we do that? Why 2 standard deviations? Why not 3? Why not 1? What is the statistical significance of the value of the standard deviation in comparison to the data? Well, let's go into that a little bit in this piece. Well, it turns out that this calculation of the standard deviation is good for only one particular type of data, and that's the type of data we call continuous data. Continuous data. That means data that's measured, usually measured with a tool. So in this instance, turnaround time, we could have measured these times to the fraction, to the millionth of the minute, to the femtominute if we'd wanted to be very, very precise. And in theory, there could be an infinite number of, uh, of possible turnaround times in our data set. So let's say that we charted a large number of turnaround times, that we charted thousands of them. We recorded thousands of turnaround times. We would expect that those turnaround times would vary around the mean, around the average of 25 minutes, that they would vary with some predictability. And in fact, many statistical processes do, and they follow something called the bell-shaped curve. Now, not everything follows a bell-shaped curve, and in fact, most variables, if you really look closely at them, do not follow a strict bell-shaped curve, but we're going to assume that these continuous data do, and we assume, our assumption is called, we assume that it's going to be a normally distributed, normal distribution, or if we want to be really fancy, we say Gaussianly distributed. Gaussian, G-A-U-S-I-A-N, Gaussianly distributed. So let's just make those assumptions that our data are normally distributed. So if our data are normally distributed, then large data sets will conform to this bell-shaped curve, meaning that the average, 25, would be here. Now my bell curve that I drew is not perfectly symmetrical, but let's pretend that it is, that it's perfectly symmetrical. So what that means is that 50% of our observations would be on either side. It would be 50% on this side and 50% on this side. So what did I really mean by that? Well, if this is the value 25, which is the mean, then there will be the number of values that are 26 will be represented by this area here, the number that fall between 25 and 26. will be represented by an area there. The number that fall between 25 and 30 will conform to this area, and so on. And so we can see this bell-shaped curve as really representing something we might call a density distribution. What do we mean by that? Distribution. It's a density distribution because we would expect 50% of the values of any observation. If we went and measured a turnaround time in the operating room just now, we just measured one, would have a 50% chance of being greater than 25 and a 50% chance of being less than 25. Well, what would the chances be that it would be greater than 30 or less than 30? Well, we can actually use the standard deviation, it turns out, to help us understand that, those probabilities. Okay, so here's a little better drawn version of our density distribution, and 50% of our values are going to be on either side of the mean. Now in this case the mean is 0. I'm using a little bit different variables here, but stick with me. So if we now draw a line that's one standard deviation, or 1 sigma, from the mean on either side, 1 standard deviation in this direction, 1 standard deviation in this direction, then that area of the density distribution will account for 68.2% of all the expected variables. So a variable has about a 68% chance of being within 1 standard deviation of the mean. So this can help us to predict what the performance of our turnaround time process will be. Furthermore, if we put the line at 2 standard deviations, then we'll have a 95% chance of encompassing the variables if they are in fact normally distributed, and only a 2.5% chance, roughly 2.3% chance, of being on the low side, or of a variable being on the high side. If we go on to 3 sigma, we only have 0.1% chance of a variable being lower than 3 sigma, and a 0.1% chance of a variable being higher than 3 sigma. So going back to our turnaround time process that we've been working with right along here, if I add these two posts here indicating 2 sigma, these are 2 sigma from the mean on either side, then that would mean that here we're at 33.4 and here we're at 16.6. So what does that mean? That means that we would expect 95% of the variables to be within this area, to be within 16, from the area from 16.6 to 33.4. What else would we expect? Well, we would expect that only 5%, roughly, of the variables would occur in these areas here, in the tails. Okay, so that's why we bother to calculate sigma, and it's how we use it. Now, how many sigma you place your control limit from the mean is an important consideration, and let's talk about that next. So before we go any further, though, we need to define types of variation. There are going to be 2 types of variation that we're going to talk about. So-called random variation, random variation. Now, random variation is what we noticed in our data set. Okay, we noticed that data distributed itself around the mean. There were more frequent observations closer to the mean and rarer observations away from the mean. This is part of nature. It's part of the nature of business, part of the nature of processes. Nothing gives the same exact, precise result every time you do it. We calculate sigma to understand exactly how broad the random variation is. The other kind of variation, the kind that we're particularly interested in identifying is so-called special cause variation. Some people call this special cause. Let's try that again. Special cause variation. Special cause variation. This is non-random. So our random variation tells us about the capabilities of our process. Special cause variation tells us when things are broken. If we're looking to establish a performance limit for our process, we would want to understand random variation. Having established our performance limits, then we would want to look for special cause variation to know when our process is broken or when some rule violation is going on. So how do we use our sigma, our standard deviation, to understand this? Well, the chance that an observation of 35 minutes, which would be here, be an observation that would occur somewhere up here, 35 minutes. Okay, the chance that that is due to random variation, that chance of a 35-minute turnaround time is due to random variation, is somewhere in the neighborhood of 2.5% or less. It's less than 2.5%. Okay, so that doesn't mean that it's not random variation. It means that it's unlikely to be random variation. So we can identify now a type of error we can make called a type 1 error. So a type 1 error occurs when we mistake random variation for special cause variation. So if we happen to have one observation of 35 minutes and we interpreted that as special cause variation, and we shut down our process and started a whole new process control measure, whole new process improvement project to deal with this one variable, chances are we're making a type 1 error because we've mistaken random variation for special cause variation. Now, how does where we place our sigma process control lines affect our chance of making a type 1 error? Well, obviously, the farther we place these lines away from the mean, the more sigma we encompass within the control limits of our process control chart, the lower the risk of making a type 1 error. Okay, if we now go out to 2 sigma, meaning that we have a 99+% chance, and we encompass 99 plus greater than 99% of all of our variables are within our confidence intervals or our process control limits, our chance of making a type 1 error is very low. But it turns out that our chance of making a type 2 error, as you may have anticipated, goes up. And what do you think is type 2 error? Well, type 2 error is mistaking special cause variation for random variation. So it may be that we have a number of observations, if we pick 4 sigma, and we're way out here at, we have, 12.8, that would be 3 sigma. We have 16.8 units away from 25, so 4 sigma control limit. Well, chances are if we start seeing a lot of 35s, we will misinterpret those as being within our control limits when in fact they are not, and we would have made a type 2 error. In general, we're more willing to make a type 1 error than a type 2 error. And that's because of this willingness, type 1 error is more common. We have a practical term for type 1 error. It's called tampering. Tampering with the process. We don't want to tamper. We don't want to mistake that 135. We don't want to stop our process with